Hi, I'm Alistair. I'm a games designer, and like many of you watching this around the world right now, I guess I'm currently in isolation here in the UK, so I'm trying to work from home, but I've also got my kids to look after and attempting to home educate them as well. So that's a whole new interesting set of challenges for me. Um, but I'm also just trying to keep my own sanity and keep the kids calm and give them something to do and distract them from everything that's going on right now. So I was trying to think of kind of interesting STEM related projects that we can all do together, and this is something which I made yesterday, which I want to share with you what it is, and so you can build something similar yourself. So my kids are all into like science fiction at the moment, Doctor Who, and kind of all things like that, and this is a toy inspired by that, I guess. This is kind of like a science fiction material analysis machine or something like that, some kind of complicated analyzer thing. So what happens is there's a little pot here which comes out, and the idea is that the kids will go and find something to put in here. It could be a piece of fluff, it could be something invisible, some sample from the air, it doesn't really matter, from an alien planet or whatever that they need to take a sample of. And they insert that into the box there. Obviously then turn the analyzer on. We'll get a little beep and a display readout. And then what they do is they press the analyze button, and it begins to scan the sample. We can adjust the wavelength here, which kind of changes the color frequency there. After a few seconds we get a result. So the substance there was collapsium apparently. And then you can take it out and put some more stuff in and do a new analysis on that. Obviously wiggle the dial again, get some pretty colours, and this time hopefully we'll get a different material. Yeah, so that was arcanite apparently. So this is just kind of technobabble. They're made up words. It has no scientific function whatsoever, but I hope it would just provide a bit of kind of escapism and imagination for everything that's going on at the moment. So here's how I built it. I started off with one of these boxes. This is a craft box which is sold from a company called The Works in the UK, but to be honest you could use a cereal box or a cardboard box, it would be just fine. And obviously I started off by just kind of painting that silver very quickly. Not a great paint job either, but this is not intended to last. And then obviously I can't go out and buy any new electronic components at the moment, so I was kind of just gathering up stuff which I had lying around. Now I'm very lucky in that I've got a reasonable stock of stuff available to me anyway, so I could find things like an old arcade button, a switch, some LEDs, a slider dial and an LCD display. And inside, if I flip this up, I can also show you there's an Arduino, and I've got a buzzer here which is making some sound effects. But there was no particular thought gone into these components. I literally just wanted to get a selection of different kind of interactions which you could do. So if you've got this stuff lying around, great. If you haven't, I promise you can make up stuff that will do very similar things using whatever you've got lying around. You can, punch holes and put a pencil in there, or some kind of slidey dial made out of cardboard. It really doesn't matter. It's just to try to get that sense of a complex machine, I guess. And I mean, again, so I then engraved just some labels and kind of abstract science fiction designs on the front. You could paint those on with a pencil or a pen just as easily. So I'm not saying that this is like the best design, this is just what I had to hand, but hopefully this can encourage you to get some ideas of what you could do in a similar setting. The interface I've got is being controlled by an Arduino Nano here. And here's how I've got that all wired together. So I've got my Arduino in the middle here, and then I've got the various components around the outside. So let me just sort of talk through each one. We'll start with the power supply. So here in the corner I've got a 4 AA battery pack. So if we assume that each of those AA batteries is giving out 1.5 volts, then this could give out a maximum of 6 volts when those are all fully charged. Now, we normally think of the Arduino running at 5 volts, and indeed all of these other components around the outside run at 5 volts as well. So what I'm doing is I'm taking the positive line from the battery pack. I'm going through this switch on the way, and then I'm going into the V-in socket on the Arduino. So V-in comes before the onboard regulator of the Arduino, and that can accept voltages of up to about 12 volts in fact. So if you've got a power supply here that's higher than 5 volts, I'm going to take that into the V-in. The onboard regulator on the Arduino is going to reduce that down to 5 volts, and then all of the other components I'm using, you'll notice, are taking their positive voltage from the 5 volt line here. So I've got a line coming in that's higher than 5 volts, that's this one, and then coming out, this is after it's been through the regulator, so everything else is getting a regulated 5 volt supply. The switch itself, so this is just a simple toggle switch that is going to, when it's in one position, it's going to connect this line here and everything is going to receive power. When the toggle switch is flicked off, we go to this leg instead, which obviously goes nowhere, so that's going to break the circuit and nothing will receive power. So that's our on-off switch there. Up here, this is my LCD display. Now, this is a 16 characters long and 2 characters high display, and they commonly have a whole line of inputs here, but mine has got what's called an I2C backpack on the back. So this is a really handy way if you're using these kind of displays. I highly encourage you to get one that comes with an I2C backpack. What it means is that in terms of the interface to the Arduino, I actually only need 4 pins. I've got ground and 5 volt, as I mentioned earlier, and then I just use a data and a clock line. So the I2C interface always uses pins A4 and A5 on any Arduino. So the clock line, that's this yellow one here, that goes to A5 and that might be labelled SCL. The data line, that goes to A4 and that's labelled SDA. So that's nice and simple if you use this thing that comes with the I2C backpack. And then at this end, the backpack deals with translating these 2 signals here into what's required by the display itself. Over here I've got my arcade button. That's a nice simple connection. It has a single GPIO pin. I'm using pin A2 here. There's no need for it to be an analog pin, it can be any pin. It just happens that that was on the right side of the Arduino for me. And I'm wiring it through to ground as well, so that when this button is pushed in, and this is going to be the button that we actually press to do the analysis, we can tell that this pin here, A2, has been pulled low because it's been connected through to ground like that. Down here I've got my slide potentiometer, so this is my wavelength modulator apparently. And the way that these work here, so I've got a ground going to one end of the slide, I've got 5 volts going to the other end of the slide, and then as you move the slide from one end to the other, you can take a reading from this pin here, and this is going into A7 in my case. So this time it does need to be an analog input pin. Like I said, when the button, we could have used any pin. I just happened to be using an analog one. But this one actually we do want to take an analog reading because we want to know how far along the scale this slider has been moved. And we'll get that by doing an analog read from this line here that comes in the middle of the potentiometer. Here we've got a buzzer, and I'm wiring that to pin D4 and to ground. Now again here there's a slightly limited choice of which pins you can use. When you want to create different tones on a buzzer, we use something called pulse width modulation, or PWM, and that's kind of like a way of very quickly turning the signal on a digital pin on or off at a particular rate, and that's how we create different tones on the buzzer. Now only certain pins are PWM enabled on an Arduino. I'm trying to remember this off the top of my head. It's something like 4, 5, 6, 9 and 10 maybe. You can check in the documentation, but 4 is definitely one of them, so that is why I'm using 4 as the input to one wire there. And again we got through to ground on the other side. And then finally here, this is my ring of LEDs which I've got going around the little sample pot. So this is commonly referred to as a Neopixel ring. The actual chip is something called a WS2812B, and these are individually addressable LEDs. So they have, once again, a 5-volt and a ground supply, and I've also put a capacitor across the ground and power lines there, quite close to the LEDs. That's just so that when they are all turned on, this capacitor can help provide, so there's a bit of a rush of in current into the LEDs there when they first activate. So it's always a good idea just to have a capacitor close by your pixels, particularly if you've got a lot of them. I mean, I haven't got too many here, but it just helps to address that initial current when they're activated. And it has a single data line as well. This is how the Arduino is going to send the signal to say which LEDs to light up. And that has got a resistor. This is a 330 ohm resistor here, and that is then going into digital pin 2 on the Arduino there. So that's all my components. Like I said, this is what I happen to have lying around. I wouldn't go out of your way to particularly buy these. If you have other buttons, levers, dials, switches, rotary knobs, it doesn't really matter. I would use them instead. But that's how mine are all wired. And then I loaded Inkscape and kind of designed how I want the front of the box to appear. So I changed my document properties first of all to the width and height of my box. So rather than laying out for A4 paper, I now know that the boundaries here are the edges of my box. And I kind of positioned where I wanted each of the components to be placed. And then sort of created these outlines first of all, and then sort of added a little bit of decal decoration using kind of abstract lines and circles. I downloaded this nice free science fiction-y kind of font as well, just to sort of label each of the components, because I sort of thought that made it look a little bit nicer as well. And then, like I say, on mine, I sent this to a laser to engrave it on the box. But if you haven't got access to that, you could just as easily send this to a printer and then use a Stanley knife or a pair of scissors to kind of cut out the holes for each of the components and just stick it on top of your box. That would have worked just as well if you don't have access to a laser engraver. And here's the code that's running on the Arduino. So we'll start off at the top with some definitions. First of all, we're going to define a value, which is the number of LEDs in that ring going around the sample chamber pot. So you can buy Neopixels with various number of LEDs in a ring, and mine has got 16 here, but you can change that if yours is different. The second define I've got is not a value, it's actually a calculation, as it were. So a bit later on in the code, we've got an array called elements. So that's here, and this is actually going to be the string values of our sort of technobabble nonsense answers. And what this define at the top does is it's going to give me the number of elements in that array. So it's going to do that by telling me the size of the array divided by the size of just one char pointer, so one character in that array, one element of that array, sorry. That's going to tell me the total number of elements I have here. Now, sometimes in my code before, I could have made that a hard value, so I said number of elements is whatever, 20, and then every time you add another thing onto the end of the array here, you have to go back and remember to update it and say, okay, number of elements is now 21. If you define it as a function like this, what it means is that I can call this at any point in my code later on, and it will tell me the number of elements that have been added to this array without me having to remember to go and update it. That's the only reason for doing it like that. Okay, and then we have some includes. So these are external libraries that are going to add some extra functionality to our code. The first one is the wire library. This comes with the Arduino IDE, and it allows you to interface with I2C devices. So in our case, that is the LCD display. And so that's a generic library for any I2C modules. This is a particular library just for using LCD displays. You can install this by going to the Arduino library manager here, and if you search for liquid crystal PCF 8574, you'll get that come up. So you can install that there. And I'm also using Fast LED. So this is a wonderful library for interfacing with all kinds of LED strips. So this is going to use, or it's going to provide us with lots of useful functions for controlling our ring of LEDs. Okay, then we get on to the constants. So these are values that are not going to change throughout the code. So first of all, we define all the GPIO pins that we've got our various components connected to. Again, obviously, if you're using different components, you can change these as appropriate, but this matches the wiring diagram I just showed you of what I'm using. And here's my array of kind of just you know, interesting nonsense words, whatever you want to call them, that I just sort of made up basically just because I thought they were funny. But you know, maybe you want to do this differently. Maybe you want to have a device which identifies, I don't know, alien creatures that are found or something like that. So you could change these names rather than sounding like material elements like collapsium and calculon and blastoline. You could change them to more like Pokemon kind of names, you know, names of monsters and things like that, whatever you want. But it's just, you know, something a bit light-hearted basically. We're going to the globals, so we declare an object that we're going to use to control our LCD display, and all I2C devices need to have a unique address. That's how we are able to communicate with them. My LCD display is on 27, that's its address, or you know, the hex address 27, and that works for me with that particular style of board. You might find you have to change that value, and there's something you can get called an I2C scanner, which if you're not sure, if you try this basically and your LCD doesn't work, it might be because it's on a different address, and you can download something called an I2C scanner sketch that will scan your I2C interface and tell you what the correct address to use is instead. But that works for me. We'll create an array of LEDs, and we'll also define a global variable for the current hue. So when someone slides that wavelength modulator slider, what it does is it changes the hue with which the LEDs in the ring are being lit up. So we'll keep a value of what hue we're on at the moment, so we know what colour to draw the next LED with. And we'll go to the setup function, and we just need to initialize all our various devices now. So our button is going to be an input pull-up, because if you recall back to the wiring diagram, it's connected to a GPIO pin and also to ground. So by default we want it pulled up to 5 volts, and then when the button is pressed we're going to pull it down to ground and it will read a low signal instead. We'll initialize our LEDs. Remember we told it how many LEDs we had at the top of the code, and this is the type of LEDs we're using, this is the data pin that they're connected to, and this is the array of LEDs which we defined just up here. We'll initialize the I2C interface, so that wire library that we included, we'll just start that interface up, and having done that we can then initialize the LCD. So we'll say that it is a 16 characters wide, 2 characters high. We'll turn the backlight off and we'll just clear it out to start with. Now we don't really need to initialize the audio as such. I probably used the wrong word there. In fact, I've put a typo in anyway. This is more sort of testing the audio. So basically this is just going to make a little beep when the code starts up. So we'll set the piezo pin as an output pin, and we'll just send a tone signal to that pin. So this is going to be a concert A, because 440 Hertz is a concert A, and it's going to be a second long. So we'll just play a second long A note when the code first starts. And finally, we're going to be using a random function later on to choose which of these values we're going to display as the result. And when you use any kind of random functions in the Arduino, you need to select a seed from which to start your random number generator. And the best way to do that is to take an analog reading from an unconnected analog pin. What that will do is give you a kind of a reading of background noise just from whatever environment you're in at the moment, and it's perfectly good enough for most functions that you're going to be using an Arduino for. Certainly for any kind of games and things like that, that's a perfectly good random number generator. So we'll set the random seed based on a reading of an unconnected analog pin, and in our case A0 is unconnected, so that's fine. And then we go on to the main program loop itself. So basically not much happens unless we actually press the analyze button. So when we do that, what happens is a digital read of button pin goes low because it's been connected through to ground. And what we'll do in that case, we'll play a sound effect. That comes from our sound FX function, which we haven't got to yet. That's at the bottom. So let me quickly talk you through this. So what I wanted to do here is I wanted to kind of recreate like a kind of a Doctor Who's sonic screwdriver type sound effect, if you're familiar with that. So it's a kind of a wibbly science fiction sound effect. And I wanted it to be slightly random as well, because I wanted it to sound like it was kind of scanning, you know, this material somehow. So what I've done is I created a delay in microseconds based on the time that the code has been running. So again, this is to get an element of randomness. When you press the button, we'll take the elapsed time that the code has been running for in milliseconds. That's what this function gives you. We'll divide by the desired periodicity, and we'll take the sine of that, and then we'll add on the amplitude, add on 2. This is basically just a function that gave me a nice sounding result, if I'm totally honest. So don't worry too much about the exact maths that's going on here. The most important thing is that it has an element of randomness called by the fact that when you press the button, it chooses a time based on how long it's been rushing for. And what we'll do then is we'll create a wave and send it to our piezo pin. We'll call high and low very quickly. We'll oscillate between them, and we'll use this delay value that we calculated up here in between each time. So again, don't worry too much about that. This has not got a very strong grounding in acoustics or audio. What it is this created a nice kind of squelchy science fiction sound effect. Is where I got that from. Okay, let's go back to the top. So when the analyze button has been pressed, first of all we play a squelchy sound effect. We'll put some text onto the LCD display, so we'll turn the backlight up now so we can see what it says, and we'll write analyzing onto the top of the screen. And then what we do is we'll sort of we'll loop over a number of times. I said 5 cycles, so this is how many times are the LEDs going to go around that ring before we determine what the material was. I could have made that random as well, I suppose. So you could make kind of some analyses take longer than others. That might have been quite fun to do, but at the moment it's fixed to 5 times each. And on each time round, what happens? Well, again, we play another random sound effect, so we have a squelchy time each time it goes round. And then we loop around the LEDs in the LED ring. So we loop around all of them from 0 to the number of LEDs. We'll read the current slider value. So remember I said we'll take an analog read from that linear potentiometer that's somewhere between 0 and 5. That, when you take an analog reading from it on the Arduino, gives you a value between 0 and 1023. So that's after it's been through the analog to digital converter on the Arduino. But we don't want a value between 0 and 1023. We want a value between 0 and 255, because what we want is a single byte value that's going to represent our hue. So we'll use the map function. So it's all a bit complicated here, sorry. So we took a reading of where the slider was. That gives us a value between 0 and 1023. Then what map does is it's kind of like a scaling function. So it says, okay, so rescale this value, which used to lie somewhere in this range, and rescale it so it now lies somewhere in this range instead. That will give us a hue that was, you know, if the slider is all the way over to the left, it's going to give us 0. And if it's all the way to the right, it's going to give us 255. we'll then create a color value based on that chosen hue. We'll assign it to the current LED. So we're looping over all the LEDs. That's what I is doing. It's going from 0 to the number of LEDs. And we'll assign the ith LED in that array to whatever that hue was. And then we'll kind of fade out all the other ones. So what we want is kind of like a trail of LEDs that go around of a particular color while all the other ones behind it kind of fade out. So that's what this fade to black by. And that's a function that's defined in the fast LED library. So that's not defined in the code here anywhere. So we do that, and we do all that 5 times while this is the analysis going on. And then when we get out of that, well, that means that the analysis is finished. We've worked out what it is, so let's display the result. So this is where we choose a random element from our elements array. So we'll get a random value somewhere between 0 and the total number of values in that array. We'll pick one, and we'll assign it to this variable here called result. Then we'll display the result on the screen. So on the top line, we'll actually say the word result. And on the second line down, we'll display what that variable is, that result there. And we'll play another A this time, so another 440 Hertz A for a second long, just to announce the fact that we've got a result for the scientist that was conducting this experiment. And then we'll continue to let all the LEDs, so we've finished analysing, but we won't immediately turn the LEDs off. We'll let them fade out again. So we'll just loop over 100 times. We'll just fade the LEDs slowly out. Then we'll clear the LED. We'll turn the backlight off again to conserve power. And finally, this might even be unnecessary, I think, because by the time we've done this, they should be fully faded out. But just in case they're not, we'll just add an additional code at the bottom there, and that's it. That's the whole lot. So there you go. That's my kind of first little project, which I'm using, like I say, partly for my own benefit to give me something to do, partly hopefully because the kids have enjoyed helping me design and sort of play with it as well. And maybe if people want to see more of these, I'll come up with some more ideas over the coming weeks and months, because we might have a little while of this to go yet. So thanks for watching. Stay safe wherever you are. Look after each other, and I'll see you again soon. Okay, cheers. Bye.